Today, we're diving into the world of the invisible engineers who work in orbit. We're talking about the AI systems that act as digital detectives, hunting for the tiniest clues of failure in satellites and drones long before disaster ever strikes.
So let's just start with a massive question, right? How in the world do you fix a satellite when it's screaming through space at over 17,000 miles per hour? The short answer? You just can't. Well, not easily anyway. And that's why prediction and prevention are everything.
And this number? This is exactly why we're even talking about this. Get this, a staggering 41% of all satellite failures happen within their first year of operation. That is a huge, incredibly expensive gamble for missions that cost millions, sometimes billions of dollars.
So that huge failure rate, that creates what engineers call the high-stakes failure problem. And preventing these early breakdowns isn't just about saving a ton of money. It's about making sure everything from our GPS to global communications actually works when we need it to.
Okay, so how did we deal with this problem, back in the day? For decades, the approach was pretty simple, if, let's just say, a bit clunky. Let's take a look at the old, bulky solution.
The traditional way of thinking was all about something called hardware redundancy. The whole philosophy was dead simple. If you think a part might break, hey, just pack a spare. If the main gyroscope fails, no big deal. You just switch over to the backup. It's basically like carrying a spare tire in your trunk.
But that whole pack of spare logic, it just doesn't work anymore. Why? Because today's satellites are getting tiny. We're talking nanosatellites the size of a loaf of bread. Same goes for UAVs or drones. There's just no room for big, clunky spare parts. So that old way is out. We need a totally new playbook, a smarter, software-based solution.
And that new playbook, that's where our heroes for today's story come in. So let's meet the digital detectives. These are the advanced AI algorithms designed to find the breadcrumbs of failure before it can bring down a whole mission.
But, every good detective needs to know their adversary, right? So before we see how they operate, we gotta understand the bad guys they're hunting, the faults. And it turns out they come in a few different flavors.
First up, you've got abrupt faults. These are the really dramatic ones. Think of a cable just snapping, or a circuit instantly frying. There's no warning, it's just boom, sudden, catastrophic failure.
Then there are the incipient faults, and these are the complete opposite. They're these slow, sneaky failures that just creep up on you over time. It's like a component slowly wearing out over months or even years. They're super subtle and way harder to catch.
All right, next up are transient faults. Now these are weird. They're these temporary little glitches. A sensor might just go haywire for a second and then, poof, it's back to normal. Could be a one-time thing, maybe caused by a solar flare, or it could be a warning sign.
And that leads us to maybe the trickiest, most deceptive ones of all, intermittent faults. Remember that weird little glitch we just talked about? Well, what if it keeps coming back again and again? That's an intermittent fault, and it's a huge blinking red light that something much more serious is wrong under the hood.
Okay, so we've got our 4 types of faults, our 4 culprits. The big question is, how do our digital detectives actually track them down? Well, it really comes down to 2 different philosophies, 2 different schools of thought. So let's break down these 2 types of detectives. On one side, we have the architect. This is a model-based approach. The architect knows the system's design inside and out, works from a perfect digital blueprint, and looks for anything that deviates from that plan. On the other side, we have the profiler. This approach is totally data-driven. It's more like a street-smart detective who's seen it all and learns to spot suspicious patterns by looking at millions of old case files. So let's dig into the architect's method first. This approach is all about having an incredibly precise mathematical model of the satellite, what we call a digital twin. This twin knows exactly how every single part is supposed to behave in any situation.
And the process is pretty straightforward, really, just 3 steps. First, you build that perfect digital twin. Then, you're constantly checking the real satellite sensor data against what the model says should be happening. And finally, you look at the difference between reality and the prediction. They call that the residual. If that residual gets too big, bam, an alarm goes off, a fault's been detected.
But, and this is a big but, the architect has a major weakness. This quote from the source material absolutely nails it. The main drawback is their requirement for precise models that are not always available. The bottom line? The architect is only as good as its blueprint. If that model is even a tiny bit off, you get false alarms, or even worse, you miss a real fault.
And that is the perfect cue for our other detective, the profiler, to step in. See, the profiler doesn't really care about blueprints. This approach is all about learning from experience, directly from the data itself.
So how does the profiler do it? Well, you feed it a mountain of sensor data from both healthy operations and past failures. Then you let an AI, usually a neural network, just sift through all of it. The AI learns to spot these incredibly subtle patterns that show up right before something breaks. It basically treats the whole satellite like a black box. It doesn't need to know the physics, it just learns that this specific pattern of data almost always means something bad is about to happen.
So okay, we've got these two really powerful approaches, the methodical architect and the street-smart profiler. But what does the future look like? Where is all of this technology heading? Let's jump into our last section.
This chart here tells a really fascinating story about where we are right now. Look at the bar for single machines. One satellite, one drone. The data-driven AI methods, the profiler's approach, are hugely popular. Over half the research is focused there. But now, look at the bar for teams of machines, like satellite constellations or drone swarms. Whoa, that number just drops off a cliff, all the way down to 7%.
And that really is the big takeaway here. For a single machine, the AI detectives are taking over. But the next great challenge, the next frontier, is teaching them how to diagnose problems in a whole team. It's so much more complex. Is one drone actually broken, or is it just getting bad info from its buddy, making it look broken? Answering that is the key to unlocking truly autonomous, self-healing swarms.
So all this leaves us with a pretty mind-bending question for the future. We've seen how smart these digital detectives are getting, but just how smart can they get? Could we reach a point where they can predict every single failure before it even has a chance to happen? A future with absolutely zero surprises in space. It sounds like something out of a movie, but as these AIs get better and better, that future is getting a little bit closer every single day.